The modern electrical grid is a system of unprecedented complexity and control. It is woven together with more sensors, automated controls, sophisticated predictive algorithms than at any point in history. Every minute, vast streams of data are collected and analyzed, tracking the flow of electricity from power plants to homes to businesses. Grid operators use this information to make constant, real-time adjustments, balancing supply and demand, with a precision that would have seemed impossible just a few decades ago. This intricate network of technology and oversight is designed for one primary purpose: to maintain a stable and uninterrupted supply of power across entire regions and even continents. Despite this remarkable technological advancement, large-scale power outages continue to occur. These events, often referred to as blackouts, affect millions of people, paralyzing cities, causing significant economic disruption. The system designed for ultimate stability still demonstrates a surprising fragility. We have built a grid that is smarter and more responsive than ever before, yet it remains vulnerable to sudden and widespread collapse. This presents a clear contradiction. If our electrical networks are equipped with more protective measures and intelligent systems, why do they still fail so catastrophically? Instead, it points toward deeper, less visible dynamics at play within the system itself. Understanding the true causes of grid instability requires looking beyond the immediate triggers, such as equipment failure or severe weather. The challenge lies in uncovering the hidden forces that can turn a minor local disturbance into a cascading, system-wide failure. The silent mathematics governing the flow of power, combined with economic pressures and operational incentives, creates conditions where instability can quietly build up, unseen by the very systems designed to prevent it. To comprehend why blackouts persist in our technologically advanced world, we must first explore the intricate system that powers it and the subtle tensions that exist just beneath its surface. The electrical grid is not a single entity, but a vast, interconnected system composed of several distinct yet dependent parts. At its very foundation are the power generators: nuclear power plant, coal-fired power plant, wind farm, solar farm. Each type of generator has unique operating characteristics, costs, and response times, contributing a different piece to the overall energy puzzle. Their primary role is to convert various forms of energy into electrical power, which is then injected into the network. These producers are often owned by different companies, competing and coordinating within a complex marketplace to sell their power. Once generated, electricity must be transported over long distances. Transmission is handled by a high-voltage network of power lines and substations that acts like the grid's interstate highway. This lets remote generation serve dense urban centers hundreds of miles away. After traversing the transmission lines, the electricity enters the distribution system. Voltage is stepped down at local substations, delivered through smaller power lines to individual consumers. Homes, schools, factories. This physical infrastructure forms the backbone of the grid: wires, towers, transformers. Overseeing this flow are the grid operators. They are the central nervous system of the network. They are often organized as regional transmission organizations or independent system operators. Their mission is to maintain grid reliability second by second. They forecast electricity demand. They schedule power generation from various sources. They manage the flow of power across transmission lines to prevent overloads. To do this, they operate within a framework of rules and procedures established by regulators. Regulators are government bodies that set policies to ensure fair practices and long-term reliability. Finally, the system includes consumers and the markets that connect them to producers. Large industrial facilities, individual households. The electricity market is the platform where power is bought and sold. Prices can fluctuate dramatically based on supply and demand, weather conditions, and fuel costs. Together, these components, generation, transmission, distribution, operators, regulators, and consumers form a coupled system where one part's actions directly influence all others. The electrical grid is governed by a simple, unforgiving law. Generation must precisely match consumption at every moment. This balance is reflected in the grid's frequency, which in North America must hold steady at 60 Hz. Traditionally, the physical inertia of massive spinning generators provided a crucial buffer, slowing down frequency changes during a disturbance. But as renewable sources like solar and wind replace them, this inherent stability decreases, making the grid more fragile and sensitive to disruption. When blackouts occur, the immediate causes are often obvious: severe weather, aging equipment, or even human error. A storm can be a catalyst, but it doesn't explain why one grid fails while another survives. A single equipment failure can trigger a cascading collapse, but that raises a deeper question. Why was the system so vulnerable in the first place? To understand the root causes of fragility, we must look beyond the surface events and into the grid's hidden dynamics. Beneath the physical infrastructure lies an invisible system that has a profound impact on grid stability: the electricity market. This market is designed to find the lowest cost power. But this constant pursuit of the lowest price creates perverse incentives. When price signals prioritize only immediate cost, they can steer the system away from physical robustness toward a cheaper, more fragile state. This fragility is compounded by an automation paradox. Automated safety nets, acting in isolation, can collectively unravel the grid they are meant to protect. Instability also emerges from the collision of fast and slow-moving systems. The grid of today reflects planning decisions made decades ago, while real-time operations must react in seconds. This underlying fragility builds up over years, like dry tinder. The system can seem stable, then a single trigger ignites the risk, causing a cascading failure in an instant. When a large-scale blackout occurs, the consequences ripple outward far beyond the simple inconvenience of darkened homes. The economic costs begin to mount from the very first minute. Commercial activity grinds to a halt. Manufacturing facilities shut down production lines. The loss of power silences the digital engines of commerce. The electrical grid is a foundational infrastructure. When the power goes out, the transportation network is one of the first to feel the effects. Traffic lights stop working. Subways cease to operate. Fuel pumps at gas stations can fail. Other essential services face severe effects. A prolonged outage can jeopardize the supply of clean drinking water. Hospitals may have backup generators but still must ration power. The failure of the electrical grid triggers a domino effect across vital urban infrastructures. This cascading failure shows how interconnected our modern world has become. The consequences of grid instability are not confined by national borders. The risk of a single failure cascading across an entire continent grows. This forces grid operators in adjacent, unaffected countries to take defensive measures, where the instability of one nation's grid becomes a direct security concern for its neighbors. The silent math of instability in one region thus imposes tangible economic burdens on others. Furthermore, major blackouts in one part of the world can have significant impacts on global supply chains. A prolonged outage in a region that is a major hub for manufacturing creates shortages that ripple through international markets. The once local issue of keeping the lights on has evolved into a complex global challenge of managing the intertwined risks of a deeply connected energy system, where a failure anywhere is a threat everywhere. The persistence of blackouts is not the result of a single, isolated cause. As we have seen, the common explanations are merely the surface triggers. The true source of grid instability lies deeper, in the complex interplay between the physical realities of the grid and the hidden systems that govern its operation. Incentives, feedbacks. Instability is an emergent property of the entire system. The market's relentless drive for short-term economic efficiency creates a powerful current. This system prioritizes the lowest immediate cost, often at the expense of investing in long-term resilience. These market dynamics create a slow, steady accumulation of unseen risk across the network. The blackout event itself is the final, rapid manifestation of these slow-moving pressures and hidden feedback loops. Silently, these forces guide the grid into a fragile state, vulnerable to even a minor disturbance. Ultimately, the silent mathematics behind blackouts is not just about the physics of electricity, but about the logic of the system we have built to manage it. The final insight is that blackouts are not accidents in the system. They are a predictable, logical outcome of the system's own internal logic, a consequence of optimizing for one goal, low cost at the expense of another, resilience. On one hand, there is immense pressure to deliver electricity at the lowest possible price. On the other hand, society also demands near-perfect reliability. This requires a grid with deep safety margins. It calls for paying for reserve capacity that sits idle, building transmission lines that may not be fully utilized every day. This trade-off between cheaper power and a more resilient system is the central ongoing challenge. How much more are we willing to pay on our monthly electricity bills to reduce the probability of a blackout that might happen once every few years? There is no easy answer. This enduring tension ensures that the conversation about grid stability will continue as we perpetually navigate the silent math that balances the price of power against the price of darkness. You've been watching System Atlas, exploring how the world's systems really work. Share your comments below. See you in our next episode.